In this video, we will go through all existing propulsion systems and also explore some new innovative concepts which might get unlocked in the future of our civilization. This is the complete propulsion system research tree I managed to build so far. This version does not aim to be a complete overview of all possible propulsion techniques/systems, but it names the base categories and gives a good basis. The biggest part of the graph is devoted to aerospace Earth launch systems. This is because here I have the most knowledge and it's also the area which interests me the most. Proposed in-space propulsion systems have often the disadvantage that they have to be first brought into space by Earth launch systems and cannot work on their own. Earth launch systems, in contrast, work on Earth as well as in space and are therefore self-sufficient, and are, in my opinion, the ones on which more research needs to be done. Even in-space propulsion systems, which have better performance in space, have often a large mass, which requires a good Earth launch system. I will try to explain in the video the different categories and the schematics/working principles the engine types are employing. I won't go too deep into each type, but try to explain the working principle as short and as comprehensive as possible. While going through the types, I will also tell my opinion which Earth launch systems have the most potential for the future. This video is the first version. If you know which categories are missing and have an opinion which ones are in the future the major techniques we as humans will rely on, tell me in the comments. Also, I think this type of research tree representation is well suited. It gives a structured map and something one can easily keep in mind. Secondly, it's a research tree. So if in the next years new technologies are developed, one can make simply new branches. We as civilization explore and find new innovations. But I think before one can do this, one has to explore at first the known territory. So let's start. The concepts may start simple but get with time more complex. In the first layer we have the differentiation between electric motors, internal combustion engines, aircraft engines and aerospace engines. So let's start with electric motors and internal combustion engines to get them out of the way. Electric motors convert electricity into movement. When current flows through a coil of wire, it creates a magnetic field. This field interacts with magnets inside the motor, causing the coil to spin. A switch keeps the current flipping so the spinning continues. In internal combustion engines, a mixture of air and fuel is combusted. The resulting explosion pushes a piston down. When the movement of multiple pistons is combined, it can be used to rotate a shaft, while continuing the combustion process. Let's move to the more exciting engines, aircraft engines. The most well-known aircraft engine principle and the one on which the other types are based is the turbojet engine. It takes surrounding air in and compresses it, inserts fuel and combusts the mixture. The combustion gases then enter with high pressure the turbine section. The turbine is connected to the compressor in the front and drives it. The thrust is created through expelling the high pressure gas in the end. The base principle for a turbofan engine is the same as for the turbojet. In addition, a fan is added to the front. The created bypass air volume flow increases the efficiency of the engine. This engine type is used in most commercial airplanes. In turboprop engines, the same components exist as in turbojet engines, namely compressor and turbine stages. But in contrast to the previous designs, here propeller is driven through the shaft, which creates the thrust instead of the high pressure gases. Then we also have scramjet and ramjet engines. These engines don't have any moving parts. Instead, they have to be accelerated to high speeds so that the incoming air is compressed through the channel design. Into the compressed air, again fuel is injected, and the high pressure exhaust gases are used to propel the vehicle. In scramjets, the gases stay supersonic. In ramjets, they don't. Let's move on. Like I said in the beginning, it makes sense to differentiate between in-space propulsion systems and Earth launch propulsion systems. First, let's have a short look at in-space propulsion systems. Two key ideas which were already implemented in practice are solar sails and electric thrusters. In solar sails, the momentum of photons, which is imparted on a large surface, is used to propel a spacecraft. This propulsion system can only be used near the sun. In electric propulsion, a propellant like xenon gas is used. The xenon particles are then accelerated between an electrode and a cathode. The expelled particles have a really high velocity, therefore the specific impulse is really high, but the thrust is low. In this category, a lot more theoretical concepts could be named. In further versions of this graph, they will also be included, but we will now focus on Earth launch systems. Since the main focus of the video are Earth launch propulsion systems, this tree branch is a lot more detailed, as you can see here. We start at first with the most conventional category, chemical propulsion. Here, in the first layer, it can be differentiated between solid rocket motors, hybrid rocket engines and liquid rocket engines. Solid rocket motors use a propellant grain in which already fuel and oxidizer are mixed. When once ignited, the grain burns down and the gases are expelled through the nozzle. The burning processes cannot be stopped. In hybrid rocket engines, the fuel is inside a propellant grain. The oxidizer is liquid. Through this, the engine can be throttled and the burning process can be stopped. But the engine gets through this more complicated. The last category, liquid rocket engines, is the most complex one. The first subdivision can be made here into tree propellant engines and bee propellant engines. Tree propellant engines are so complex that they deserve a complete own video for explanation. But in principle, a tree propellant rocket engine uses 3 different propellants. Typically, a dense fuel like kerosene, a high energy fuel like liquid hydrogen, and an oxidizer like liquid oxygen, burned in stages or mixed to optimize performance. This allows the engine to start with high thrust, dense propellants for liftoff, and then switch to lighter, more efficient propellants for better efficiency in later stages. Bee propellant engines use only 2 propellants, oxidizer and fuel. These engines are most commonly used in rockets. Here we have a lot of subcategories. The simplest engine is here the pressure-fed engine. The main propellants get pressurized from a third pressure gas source. The propellants are injected into the combustion chamber, burned and expanded through the nozzle. Here the disadvantages are that over time the pressure decreases and the tanks are really heavy. Electric pump-fed engines are also really simple. Here, instead of a high pressure gas, the propellants are pressurized with 2 pumps that are driven by an electric motor. Because of its simplicity and the innovation in battery technology, I think this cycle is really promising for future development. The next category is aerospike engines. The propellant can be pressurized by different cycles. Here, in the nozzle design, is the essential differentiation. Conventional engines have the problem that they never expand to the environment pressure and lose therefore efficiency. Aerospike engines use basically the environment pressure as the nozzle and therefore expand no matter the altitude 100% efficient. The last 2 categories are new innovative designs and gas-driven engine cycles. In the new innovative designs category, we have a more precise example and a general subcategory. I made a video about a combined pump turbine layout with internal turbine blade cooling, which could be used for rocket engine cycles. This is displayed in the left picture. The other category is new pressure generating devices. Here, as an example, positive displacement pumps are shown. But in principle, any possible solution for creating pressure would fit in this category. For such designs, I see a lot of potential for the future. In gas-driven engine cycles, we differentiate between open cycles and closed cycles. Open cycles are generally simpler designs, therefore we start here. In the most used conventional cycle, the gas generator cycle, 2 pumps pressurize fluid before the fluid is transferred to the combustion chamber. A portion is led into the gas generator and burned there. The created gas drives a turbine, which in turn drives both pumps. Through this, continual flow to the combustion chamber is ensured. In the open expander cycle, the fuel is used to cool the engine. While it cools the engine, it is heated and changes to the gas phase. This creates enough power to drive the turbine, which again drives the 2 pumps. In the tap-off cycle, high pressure gas directly from the combustion chamber is used to drive the turbine. In all of these cycles, the gas is thrown overboard after it drives the turbine. This is the key difference to the closed cycle, to which we go next. Here we have the closed expander cycle and staged combustion cycles. In the closed expander cycle, the fuel after it drives the turbine is not expanded in a different nozzle and leaves the engine. Instead, the fuel is fed back into the main combustion chamber, where it can be burned with higher efficiency. In the staged combustion category, we have fuel-rich, oxygen-rich, and full-flow staged combustion. The basic principle is the same like in the gas generator cycle. The only difference is that either the gas generator burns fuel-rich or oxygen-rich. This has the advantage that the propellants are partially burned in the gas generator and can be then fully burned inside of the main combustion chamber with higher efficiency. Lastly, the most complex cycle is full-flow staged combustion, which is used in SpaceX Raptor engine. About the Raptor engine, I made also a complete and detailed video. In full-flow staged combustion, two separate gas generators exist. One burns fuel-rich, the other one oxidizer-rich. Both gases, which are partially burned, are injected with better mixing efficiency into the main combustion chamber. Of course, this cycle has with SpaceX Raptor engine a lot of realized potential. Only the complexity is a disadvantage. With this, the chemical propulsion research tree is completed. We will now go over to nuclear propulsion. Here one can divide the category in the fusion principle and the fission principle. Because fusion is way less understood than fission, we concentrate here on fission. Again, one can differentiate between closed cycle and open cycle. For the closed cycle, there are three principles of nuclear thermal rockets, short NTR. In all of these cycles, atomic energy is used to heat a propellant like liquid hydrogen so that it can expand with high efficiency through a nozzle. Atomic energy sources are really dense. Therefore, the specific impulse is way higher than in conventional engines. Nuclear propulsion is mainly suitable for second stage designs. However, if an engine is developed with high enough thrust, also first stage designs are possible. In solid core engines, a nuclear reactor with heating rods is placed inside the engine to heat up the liquid hydrogen. In a Nerva rocket engine, the cycle is already implemented. Therefore, it is well understood. However, again, probably another video would be necessary to explain it in detail. In closed gas core cycle NTRs, atomic fuel in its gas phase is used to heat liquid hydrogen. In this cycle, the gas phase atomic fuel is more directly in contact with the liquid hydrogen and has higher temperatures. Therefore, the efficiency is even better. A similar principle is also used in liquid core NTRs. In all of these cycles, the radioactive fuels are kept inside the engine and are only used for heating. The radioactive material is not ejected into the environment. This is the key difference to the open cycle NTRs. In open gas core nuclear thermal rockets, uranium gas is directly mixed with the liquid hydrogen fuel. This creates extremely high efficiency and thrust. The only problem is that the environment isn't usable anymore when ignited on Earth's surface. So probably it's better not to go down that road. The same principle, only with liquid atomic fuel, is true for open liquid core engines. This completes the nuclear propulsion tree. The next category is air-breathing assisted systems. There we have air-augmented rocket engines and jet plus rocket engine combinations. In air-augmented rocket engines, the oxidizer is not carried with the engine. Instead, the surrounding air is used as oxidizer. The problem here is that at an altitude of 10 kilometers, the air is not anymore dense enough to provide a consistent mass flow rate. In the combination sections, we have scramjet plus rocket engines, turbojet plus rocket engines, and ramjet plus rocket engines. These concepts incorporate for the aircraft engines and rocket engines same liquid channels and components, but can switch between operating modes. A well thought through engine in this category is the synergetic air-breathing engine. But again, to explain the cycle, a complete video is probably necessary. We now go over to launch-assisted systems. The company Spin Launch tries to spin up a small rocket inside the vacuum chamber to really high speeds. The rocket is then released in vertical direction. This is done to give it an initial boost. The rocket itself has again another engine with a specific cycle in it. Problems are here the high rotational speed, high centrifugal forces on components, and that the initial boost is probably small compared to the overall required delta V. Another approach is to launch a rocket from a carrier aircraft from altitudes up to 20 kilometers. In this approach, the high lifting mass of the carrier is one problem. The last possibility is an electromagnetic railgun launch system. The next last sub-tree section is beamed energy assisted launch systems. Similar to nuclear thermal propulsion, there's only one propellant used. In most concepts, liquid hydrogen. The propellant is heated for expansion through a heating source that is kept on Earth's surface. The source is a laser or microwave radiation. Usable materials for the rocket and cloudy skies are here the problem. The last two categories are pulsed or rotating detonation engines and rotary rockets. Pulsed detonation engines do not use continuous combustion. Instead, pulsed detonations, which are more powerful and therefore the engine is more efficient. Lastly, the rotary rocket was an idea where the rocket is spun up during launch. Through centrifugal forces, the propellants get pressurized and no pumps or turbines are needed. Additionally, the helicopter part could be used for landing, but multiple problems exist in this design. This finishes the Earth Launch System tech tree. The research tree is nowhere near completion, but I think it's a good first version. Leave a like if you found the topic interesting and have a look at the end card for other videos if you are interested.